Good day, everyone. My name is Faoziyyah Bolomope, and I'm here today with Ashiadey Gameli and Chinedu Chukwuma to present our project, which is titled A Feasibility Study, Integrated Renewable Energy and Thermal Management System Design for a Sustainable Data Center Operation. It's a mouthful, but an interesting topic. In this presentation, we will give a brief problem statement, the objectives of the research, and the methodology that was used to achieve our objectives. Then we're going to give a brief description of our model and discuss the results of the modeling and simulation. And finally, a little bit of conclusion and recommendation. To start with, why exactly is this project interesting to us? Well, data centers are essential infrastructures that support our digital economy, from AI, ChatGPT, to IoT. A data center is essentially a network of computer servers, and these servers generate a lot of heat when processing and storing data. And as demand for this data grows, as AI continues to grow, so do concerns about energy consumption and their environmental impact. One of these systems in data center that consumes quite a lot of the energy is a cooling system, and this can account for up to 40% of a data center's total energy use. Some research have shown that advanced cooling systems like the liquid immersion cooling can efficiently reduce the heat generated. However, there are certain downfalls to this. First off is humidity control, and second off is that there's some areas where water they have water scarcity in these regions. Other researchers also explored hybrid systems which use a combination of air and liquid, and sometimes actually in Japan, even snow, to reduce the energy use of a data center. This project builds on these findings by proposing a snow-based cooling system that is powered by renewable energy resources. Our methodology consists of 4 key components. To make the simulation location-specific and accurate, we used real climate data generated from Energy Plus, NASA Power, and the Climate Data Store. These were used to analyze the snowfall in centimeters, snow volume, snow mass, the average humidity, and other metrics here in St. John's. Next, we modeled the energy demand of a data center, and this includes the information technology loads like the servers, and also loads like the cooling loads, which are like the chillers. Afterwards, we designed a renewable-based hybrid system using renewable resources to supply this demand. Then we compared 3 cooling strategies, which are the air cooling, liquid cooling, and the proposed design, which uses indirect air cooling and snow cooling. These were modeled and evaluated on the key metrics like coefficients of performance and power usage efficiency. When selecting the site, we considered a few key things like site conditions, existing dump sites, weather conditions, and the relative humidity in comparison with the Ashiadey standards for humidity, and this is about 70% relative humidity. These parameters helps us to define a safe range for fluid that is going into the data server room. And this is especially important for the kind of system design that we're proposing. We selected St. John's because it is a very ideal location for its cold cool winters and snowy summers. St. John's actually receives about 335 centimeters of snow in terms of snow depth on an average every year. And using data from the climate data store, the snow volume and snow mass were computed, and we found that the usable snow volume in a year is approximately 69 million cubic meters and over 14 billion kilograms of snow. This is enough to support a passive snow-based system for a Class 1 data center. The graph on the left shows St. John's monthly weather averages in terms of temperature and snowfall in centimeters per month. And on the right is a graph that shows the relative humidity with respect to the threshold, which is the Ashiadey standard, which is about 70%. Now, in winter months, it can be seen from the graph that the vapor pressure is low, and this means that the air is dry and can effectively absorb it, and therefore it increases like the cooling efficiency. Now, to maintain safe operating conditions for the IT equipment, this is actually a good, St. John's is actually a good weather and a good location for this. For most of the year, the relative humidity hovers like below or near the 70% threshold, and this supports the Ashiadey and confirms that the air cooling is viable for long periods, and we can use the winter air to actually cool our system and in turn reduce the energy consumption. The proposed system was divided into 3 subsystems, which we call like the system A, which is like the data server room where the thermal flow is in. Then system B, where we have our cooling snow, that's where our cooling technology comes in. Then system C is the power system unit, which will be integrated with renewable or sustainable energy resources. To determine the layout of our system in System A, we consulted a few research papers, and it is found that combining indirect airside free cooling in winter months and indirect liquid cooling in the warmer season can actually help to maintain a better indoor air quality. And this is directly related to the humidity of a system, because we would not need advanced or complex systems to control the humidity. For the indirect air cooling, an heat exchanger is used to transfer heat from the hot aisle of the server room to the cold air outside without actually mixing them, also for humidity reasons. The layout used for the server room is the hot aisle containment system, and this physically isolates the hot air from mixing in with the cool air, and this basically increases the cooling efficiency of the system. Now, when it comes to the system B, which introduces like the snow-based cooling, essentially we're using melted water from the snow, because as snow stays over time, it begins to melt. And how this works is snow collected during the winter is stored in an insulated containment area. We simulated the data center to be close to the Robin Hood Bay because it is a current dump site for snow in St. John's. Now, this melted water is pumped into the air handling unit of the data server room, where it absorbs the heat from the server room and circulates through to absorb like the cold from the melted snow. Now, system C, which is the power system unit, is an we think of it as an ideal power source whereby we have a mix of renewable resources, PV, wind power, and we use OMA to simulate which kind of renewable resources would be able to power the data center and reduce the energy dependence on fossil fuel and other types of non-renewable energies.
The data center for our simulation generates 14,000 kilowatts of heat from the IT equipment. This is comprised of 2,007 kilowatt servers. The space is to be maintained at a temperature of 18 degrees Celsius. 3 cooling modes were simulated. The first was cooling by the chilled water system only. The second was cooling by the chilled water system and free air cooling. And the third was cooling by snow melt water and free air cooling. To determine the frequency when each mode of cooling will be used, the hourly outdoor air temperature averages for St. John's was simulated over a period of a year. The green line on the graph shows the threshold, which is 18 degrees Celsius, and below this threshold, free air cooling will be used. Above the threshold, mechanical cooling will be used. It shows that free air cooling is used during the cooler months of the year, and mechanical cooling is used during the warmer summer months. To further explain the frequency within the year where each mode of cooling will be used, the graph on the left shows that free cooling will be used for 8,229 hours within the year, whereas mechanical cooling will be used for 531 hours during the year. The graph on the right shows that free cooling will be used for 94% of the time during the year and mechanical cooling 6% of the time. These tables show the designed chilled water system ratings. The table on the left shows the flow rate of water and air and their temperatures that provide cooling for the data center. The table on the right shows the power ratings of the various components of the system. The following slides analyze the results for the simulation of the various cooling systems. This slide analyzes for when only chilled water system is used for cooling. It shows that an annual electricity of 24,890 megawatt hours is used, costing over $6 million. Most of the energy is used by the chiller, followed by the air handling units and the pumps, with the cooling tower consuming the least. The system also uses over 130,000 cubic meters of water a year, costing $1,300. Most of the water is lost due to cooling tower evaporation and some due to cooling tower drift and cooling tower blowdown. This result shows a scenario where combined chilled water system and free air cooling are used for cooling the data center. The electricity demand reduces to 4,340 megawatt hours a year, which reduces the electricity bill to just over $1 million. Most of the energy is used by the air handler unit fans, followed by the chiller, then the pumps and the cooling tower. The system also uses significantly less amount of water, just below 8,000 cubic meters a year, costing $1,000. This result shows when snow water and free air cooling are combined to cool the data center. The electricity demand reduces to 3,340 megawatt hours, costing just over $800,000. The electricity is consumed by the fans and the pumps. The chiller and the cooling tower are eliminated because the cold water is supplied by the melted snow water. On the right, all the systems are compared to see the cost savings that is achievable. It shows that when combined snow and free cooling are used, a cost saving of 1,200% is achieved compared to when a purely mechanical water chiller system is used.
In this section of our work, we downloaded the solar irradiance and wind speed data using Homer Pro, the daily energy requirements, which was developed on Schneider Electric Data Center Efficiency and Power Usage Effectiveness Calculator, from where we got our data center load of 14,328 kilowatt hour. This guided us in selecting the various system components which we use for the simulation. Considering the available resources in Newfoundland, we selected a wind turbine, a PV panel, then we added the grid to our system for simulation. We simulated 4 different scenarios. For the first scenario, we simulated using PV alone. We assumed constant load, so we set our constraints to have 100% load in current time step. We also want a reliable system for the data center, so we set 0 annual capacity shortage. And then the electrical simulation result shows that we have excess electricity of 12,970,956 kilowatt hour per year, which is very high. Then we had some unmet electrical load of 334 kilowatt hour per year and capacity shortage too. In the second scenario, we simulated using wind turbine alone. From the electrical simulation results, we can see that the efficiency improved as we have only 52.2% excess electricity when compared to the first scenario. We also have 0 unmet load, unlike the first scenario where we had about 300 and something kilowatt hour, but a capacity shortage of 0.0946 existed. From this result, we can see that wind provides better round-the-clock generation, but it still lacks full reliability. Also, for the third scenario, we simulated using wind turbine and PV, and from the electrical simulation results, we see a little improvement when compared to the second scenario, with 63.7% excess electricity. We still had unmet electrical load at 0 in this configuration. The capacity shortage, a little improvement, 0.0946% when compared to the previous scenarios. In the fourth scenario, we added the grid to our simulation. The grid in Newfoundland, we considered it renewable because approximately 97% is generated from hydro. And so we added that to our wind and PV. And from the simulation result, we can see that the excess electricity generated was 0 because based on our configuration, the excess electricity will be sold to the grid and vice versa. So the grid acts as a backup when the generated power is insufficient to meet the load. We take power from the grid. And so as a result of that, we see 0 unmet electrical load and also 0 capacity shortage. Here we have the Homer Pro optimized results for the various scenarios, and it shows the net present cost, the cost of electricity, which is in dollar per kilowatt hour, the operating cost, and the initial cost. So starting with the first scenario, we had PV alone. We see that the initial cost of this project will be very high, and the cost of electricity will be high, $2.58. The second scenario where we had wind, the cost of electricity is 0.8 cents, The third scenario, we had wind and PV. There isn't much difference when compared to the second scenario. And then we see the fourth scenario where we had the grid added to our simulation. The cost of electricity dropped to 0.09 cents. And then we can also see the initial cost dropped because of existing infrastructure for the grid in St. John's. And so we see that the fourth scenario, it's a good one for the project. Here we can see the Huma Pro optimized simulation results. The wind turbine, you can see the annual production, which is far more than the grid purchases, which is just 19.3%. So we see that there is abundant wind energy in Newfoundland. And so the grid in our system is acting as the backup. So this system is clean. There's no emission. And so the results from our simulation shows that Newfoundland and Labrador, with abundant natural resources, is sufficiently able to generate clean power for the data center.
Just a little recap. This project explored the technical and economic feasibility of using melted snow and the winter air as a cooling medium for a data center here in St. John's. And the results are quite revealing because a traditional chilled water system uses nearly 25,000 megawatt hour per year, while this system only uses about 3,300 megawatts hour per year. That is so different, right? So not only does this system save energy, it saves money, and it reduces the demand on the city's water, whatever location. It reduces the demand on the water infrastructure there already. And also, by integrating the abundant wind and hydro resources available here in St. John's, we can also reduce the demand on the electricity grid by using the system. So some of the recommendations we have is that we could find a way to improve like the snow storage system in terms of thermal stability, because we don't want the snow to melt too fast, and also addressing like clogging risk, because most of the snow gotten from the dump site is a mix of debris, snow, dead leaves, and other things like that. Another thing is maybe incorporating a switching system that can predict when to switch from the snow to the air cooling. So there are other various aspects that one can do in future research, and these are just some of our recommendations. Thank you so much for listening.